Okay, so this problem is problem number 6, and we're going to answer all of question A together and help you out with question B, and then if you still need help, you can come see me one-on-one for question C. So it says a block weighing 80 newtons rests on a plane inclined at 20 degrees to the horizontal. The coefficient of static friction is 0.25, while the coefficient of kinetic friction is 0.15. Now, just a note about this, the coefficient of static friction, this is a variable force, so when it does say this is the maximum coefficient of static friction. At this point, if you get a force that would be equal to the normal force times 0.25, this is when it would start to budge. It would no longer remain static, and then it would jump down to 0.15, which is your coefficient of kinetic friction. All right, so what we're going to do for part A is we're going to start with a force effect diagram, and we're going to determine why we need the applied force T. Okay, so I'll just say my block is right here. Here's our little block. Our little block. And I'm horrible at drawing arrows, so I have to draw my own. So we should have our force that comes down. This is our weight force, basically. The force of gravity, which actually gives us 80 newtons here. It doesn't give us the mass. We've got our normal force. And then, of course, it tells us, I'm going to draw this a little bit above the plane. We have our friction, static friction force. Our normal force, I know that theta is 20 degrees. I'm just going to write theta here for right now, just because I feel like it. It's our force of gravity, which it does tell us is 80 beautiful newtons. And this is our force of friction static. Now, what it says, and I know the force of friction static is going up because it's trying to slide down the plane. So if that wasn't there, it would slide down the plane, right? And so what we have going on here is basically this problem is saying that our x component of gravity, the component of gravity that's parallel to the plane, is greater than our static friction. And we want to keep this block in place, which means we're going to have to add an additional force here. I'm going to put this force in yellow. That's a good example. Okay. And this force right here is going to be T. How much should this additional force be in order for it to not slide down the plane? Okay. So let's sum up our forces in our x direction, and I shall call this x as being parallel to the plane, and y as being perpendicular, and this is our positive direction, sliding down the plane. So it should be the force of gravity in the x direction. That should be the only thing in the positive direction. And the negative direction should be the force of friction of static and tension. And if we don't want the object to move, it should remain at rest. Okay. So now we just need to find all of these values. Okay. So let's break gravity down into its components. Okay, we have a component perpendicular to the plane and a component parallel to the plane. Alright, so this is not theta, so we'll get this one again. It's theta. So this should be our y component, which should be 80 cosine theta. And this should be our x component, which is 80 sine of theta. And so the normal force should be equal to that. And that's quite important. So let's plug in what we have so far. The gravitational force for the x component should be 80 sine theta. I'm just going to write theta here because I don't feel like writing how many degrees. I don't have an expression yet for the frictional force. I'm just going to leave it like that. And I don't have an expression for T. But basically the sum of these two forces should equal 80 sine 20 degrees or 80 sine theta, like whatever. But what do we know about the frictional force? Well, the frictional force in static, if we want the maximum value of that, that should be equal mu s times the normal force. Okay, well, that's great. I'm going to plug that in. I guess I can write 20 now. It doesn't matter. So that should be equal or minus mu s times the normal force. Still don't know what T is. Let me just bring T over since that's what we're trying to find. But I do know that my normal force should be 80 cosine 20 degrees in order for this thing to not fly off the table. And that's it. I know that mu s is 0.25, basically a quarter. So if mu s is 0.25, a quarter of 80 would be 20, so minus 20 cosine 20 degrees, and that is your t. So that means that if you look at this is 80 sine of 20. That value is much greater than 20 cosine 20. And so we need to find that additional force to compensate so that it doesn't slide down the plane like we were saying. So what does that value actually equal? Tap on the calculator. Let me make sure I'm in degrees. I'm not. I was about to yell at you guys for that, of course. And it is 8.56775 newtons. 5.67759 newtons, which is perfectly fine. Okay. Great. So now let's look at B. Now, the tough part of this is the problem changes. Okay. What's the minimum applied force T that will start the block moving up the plane now? And you might think, oh, it's just going to be 8 newtons in the opposite direction now. We still have static friction, but what has happened is, let me copy this picture. I guess so. What has happened is now it's going in the opposite direction because now it's moving up the plane. So things have changed. So again, here's our 20 degrees. Here's our block. Okay, now when we draw our forces here, you still have your normal force. You still have gravitational force, but now we want this guy to move up the plane. So static friction is actually working with the x component of gravity, the parallel component of gravity. And so T is now going to be in the complete opposite direction because now we want this guy to move up the plane. Okay, and it's when it's going to move to start to move up the plane. Okay, so we're pulling on this. We're pulling on this. At what point do we have enough force that it's going to compensate for these two forces here? So let's label these, and then let's see if you can find them on your own. So this would be the force of friction static, which remember is mu s, and this is the maximum value here. This idea of the minimum and the maximum can get kind of confusing. So you just have to think of it as a threshold point. Once you get to this maximum frictional force, that's when it'll release and allow you to, it's called the breakaway. You can break away and start moving the object. But here's the normal force. This is the gravitational force, which we said was 80. And so remember to draw your components, and this is T. So everything is moved around a little bit. Okay? Now, knowing that, you could answer part C as well. If you can do part B, you can answer part C. But notice, once it keeps moving, now it's no longer going to be a static friction. This graph should be the same, except if it's moving up the plane now at constant velocity, it's moving already. So this is not going to be static friction, it'll be a kinetic friction force. And all that simply means is you'll use the coefficient of kinetic friction. You apply a lot of force to get it moving, and then you just don't have to apply as much force. Just think about that.